Okay, so welcome to 6.1, which is growth models. Growth models. Okay, so definition. So a sequence of numbers. So a sequence of numbers let's call them capital P sub n, so is defined recursively. So that's what we're defining, recursively. So if each number in the sequence, in the sequence is defined with respect to previous terms. So it's defined with respect to previous terms. Okay, so what does this mean? So for example, let's let capital P sub n be capital P sub n minus 1 plus 7. So for any number n. So if P sub 0 is 3, find the first 5 terms of this sequence. So find the first 5 terms. The first 5 terms. Of this sequence. Okay. So of course we want to start with P sub 1. Okay, so P sub 1 by definition will be P sub 1 minus 1 plus 7, according to the rule P P sub n is P sub n minus 1 plus 7. Okay, so I claim that this is P sub 0 plus 7. And they gave us that P sub 0 was 3. Okay, so that's 3 plus 7. So P1 is 10. So now let's evaluate P sub 2. P sub 2, according to the rule, is P sub 2 minus 1 plus 7. So P sub 2 minus 1 is 1. So I claim that that's P1 plus 7. And we found that P1 was 10. This is 10 plus 7. So that's 17. Okay, so now let's try P3. So P3 will be P sub 3 minus 1 plus 7. So 3 minus 1 is 2, so I claim that that's P sub 2 plus 7. And we found that P sub 2 was 17. So 17 plus 7. 17 plus 7 is 24. So that's 1, 2, 3. We have the first 3 terms. So we want 5. So P sub 4 will be P sub 4 minus 1 plus 7. And 4 minus 1 is 3. So this is P sub 3 plus 7. And P sub 3 we found to be 24. 24 plus 7 is going to be 31. Okay, and now finally, P sub 5 will be P sub 5 minus 1 plus 7. 5 minus 1 is 4, so I claim this is p sub 4 plus 7. And we found that p sub 4 was 31. So 31 plus 7 is 38. Okay, so let's take a look at this whole sequence we have here. What color shall I do it? Pink. Okay, so the sequence we have here, P1, P2, P3, P4, P5. So P1, come on. It's a terrible curly bracket. Let's see. There we go. So we P1, P2, P3, P4, and P5. Constitute the set. What do we have? 10, 17, 24, 31, and 38. So these are the first 5 terms of the sequence. But let's note something. I claim that I can rewrite this as follows. Do you agree that this is 3 more than 1 times 7? So what I'm going to do, actually, let me write 7 times 1. What color shall I use? Pink, I'll use the pink. Okay, 10 is 3 plus 7 times 1. What about 17? Can 17 be written as 3 plus 7 times? Well, 3 from 17 is 14, and I know 14 is 7 times 2. Okay. Let's see if I can do this same pattern here. Can I write this as 3 plus 7 times something? Well, 21 would be 7 times 3. Let's do the same thing for 31. So can that be written as 3 plus 7 times, well, 28. That'd be 7 times 4, right? 28 and 3. Perfect. Okay, last but not least, can I write this as 3 plus 7 times, hopefully 4? Oh, oops, not 3. That makes no sense. Hold on a sec, let me go back. 4, because this is definitely 7 times 5 is 35. Okay. So let's note that if I were to find P sub n non-recursively, P sub n is equal to 3 plus 7 times n in non-recursive form. Non-recursive form. So that's when it's not written in terms of previous terms. Okay, so definition. So linear growth, that's what we're defining. Linear growth can be modeled by the formula. So can be modeled by the formula. P sub n is P sub 0 plus D times n, where n is any whole number, that is counting numbers. P sub 0 is the initial value, or principal value, initial value. And D is the common difference. So it is the common difference. Okay. Okay, so let's go back up here. So here, 3, was that my initial value, my given p naught, or p sub 0? Yes, it was. And what is the common difference between each of these terms? Well, to go from 10 to 17 is 7. To go from 17 to 24 is 7. To go from 24 to 31 is 7. To go from 31 to 38 is 7. So the difference between each term is 7. That's what I have here. And then n would be the counting number. Okay, so let's note that linear growth increases by the same amount each term. So note. So linear growth increases by the same amount each term. So for example, so let's plot the first 3 terms. So plot the first 3 terms. 3 terms of the sequence. Let's do p sub n is going to be, let's do -1 plus 2 times n. So this is of the form p sub 0. So I know p sub 0 is -1, and I know my common difference, d, is 2. So what that means is to get p sub 1, I just add 2. So this would be -1 plus 2. So p1 is going to be 1. I know p sub 2. I'm going to add 2 to the previous term, so it's 1 plus 2, which gives me 3. Do you agree the common difference between each term so far is 2 units? And the final will be the previous term, 3, plus the common difference, 2. So I should get 5. Okay, let's see what happens when I plot this. So x and y, or n versus p sub n. Okay, so let's say that this is the values of n I plug in. And these are the values of p sub n. So 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3. -1, -1, 2. Oh, actually, counting not my strong suit. 1, 2, 3, 4, 5. Okay, so the initial value p sub 0 was at -1. When n, the counting number, was 0. P sub 1, so my counting number is now 1, has a value of 1. So I go to the right one, up 1. P sub 2 has an n counting number of 2, goes up to 3. So over 2, up 3. P sub 3 has a counting number n of 3, but has a p sub n value of 5, so I go up to 5. And notice that if I connect the dots here, I do get a line. That's what oops, well, I'm trying to get a line. Hold on. What happened there? Let me undo this. Okay, so let's see if I can do this a bit better. This way? Okay, there we go. So there's a line that goes through them. So this is linear. Okay, so straight line through all points that means linear. Okay, so continuing on. So for example, so let's plot 5 terms of the sequence. So plot 5 terms of the sequence. Let's do p sub n is equal to negative 2 plus n. Okay, so I know the initial value p sub 0 is given as negative 2, but the common difference is just 1 if it's not explicitly written. So the d is 1, because there's always an implied multiplicative of 1 there. Okay, so what that means is when I go to p1, I'm just going to take negative 2 and add 1 to it. So that gives me negative 1. Okay, now p sub 2, the second term, will be the previous term plus 1. So I get 0. P sub 3 will be the previous term, p sub 2, which was 0, plus a common difference. So I get 1. P sub 4 will be the previous term, 1, plus a common difference, 1. So I get 2. And finally, p sub 5 will be the previous term, 2, plus a common difference, 1. So I get 3. Okay, so let's go ahead and plot these. So n versus p sub n. Growl my stomach. Okay, n versus p sub n. So we plugged in 0, 1, 2, 3, 4, 5 for n. Actually, let me double up since I have the room. So let's call this 1, 2, 3, 4, 5, and 1, 2, 3. But then I have to go down to negative 2 here. 1, 2. Oops. 2. Okay, so negative 2, negative 1, 0, 1, 2, 3. Then 1, 2, 3, 4, 5 for my counting numbers. So the initial value when the counting number was 0 was at negative 2 in purple. Then the first value when the counting number was 1 was at negative 1. The second value when the counting number is 2 was 0. The third value when the counting number was 3 was up at 1. The fourth value when the counting number is 4 was up at 2. And the fifth value when the counting number was 5 was up at 3. Okay, so hopefully we can see that this is indeed a nice straight line through here. So it is linear. Okay, so linear, check mark. Okay. So for example, suppose the entrance fee, so suppose the entrance fee to a cat cafe is $15 plus $2 a treat for each cat for each cat you want to feed. let's find a linear equation, or what's termed a linear growth model, to model this. So find a linear equation which models this. Models the cost. How about that? We'll call it that. Models the cost. Okay, so I'm going to call P sub 0 no cats. So no cats fed, just entry. Just entry. So do you agree just entry fee is $15? So P sub 1 will be 1 cat fed, 1 cat fed, fed, F-E-D, and entry. Okay, so it's $15 to get in, but then I'm going to have $2 for the 1 cat I fed. So that'll be 17, of course, but I'm just going to write it this way for a moment. So P sub 2, that's 2 cats fed, 2 cats fed, and entry. Okay, so I've got $15 to get in, plus $2 times 2 cats, right? And in fact, I could write this $2 times 1 cat up here. And if I wanted to be really explicit, I can write $2 times no cats up there, because anything times 0 is still 0. So for the third, P sub 3 would be 3 cats fed, and entry. Okay, so hopefully we can see this will be $15 plus 2 times 3. So do we see the pattern? 2 times 3 cats fed. Let's do one more for good measure. So P sub 4 would be 4 cats fed, and entry. So that should be $15 plus $2 times 4 cats. Okay, so if I were to say what is the linear model for n, that is n cats fed and entry, where n is a counting number. So I have $15 to get in, but then I have $2 for each of the n cats. So that is the formula, the linear formula, that models this business. Okay, so let's recall something. Recall. So compounded interest, compounded interest, as opposed to simple interest, takes into account the previous interest earned. The previous interest earned before calculating the new interest. Before calculating the new interest. Okay. So for example, suppose a population of 1,000 rabbits. So suppose a population of 1,000 rabbits increases by 10%. So So increases by 10% each year. So can this growth be modeled by a linear equation? So can this growth be modeled by a linear equation, i.e. by a line? So a linear equation. Okay, well, population of 1,000 rabbits. So my initial population, P sub 0, is 1,000, right? And by the way, my interest rate, what color shall I do my interest rate in? How about this blue? How about pink? So my interest rate, R, is 10%. It's 10%, which we know to be 0.10. Okay, so what is P1? Well, P1, of course, is going to be P naught, P sub 0. And then we're going to add to that 10%. 10% of P sub 0, right? So at the end of year 1, I should have 10% more than my initial amount. So I should have $1,000. It's 1,000 rabbits, not dollars. I don't have $1,000. I don't even have $10. Okay, plus 0.1 times 1,000. And why did I write it like that? I prefer not to use a calculator. Let's write that as 10 over 100, shall we? In that way I can reduce 2 of the zeros. And I get 100. So 1,000 plus 100 is, actually let me write it out, 1,000 plus 100 is 1,100 in blue. So that's how many rabbits I have at the end of the first year. So what about the end of the second year? So P sub 2 will be, well, the second year, remember I have to take into account the first year. So it's going to be P1 plus, in green, plus 10% of P1, right? 10% of P1. So that's going to be 1,100, and that should have been green here, plus 10 over 100 times 1,100. Okay, so what that gives me then will be 1,210. Okay, so the third year, let's go down here, P sub 3 will be the second year, P sub 2 plus 10% of the second year, 10% of P sub 2, which is going to be 1,210 plus 10% of 1,210. 10% of 1,210. Remember, 10% just moves a decimal over by 1, right? So we're going to add $121 to 1,210, so we get $1,331. Okay, so let's see is this linear? Well, let's note. Is there a common difference? So is there a common difference? d between each term. Each term. Well, let's see. So if I have P naught is equal to 1,000, P1, so let me move this down. P1 was 1,100. 1,100, what am I saying? Okay, so this difference is 100, right? P sub 2, however, was 1,210. So to go from 1,100 to 1,210, this difference is going to be 110, right? P sub 3, that was 1,331. So that difference will be what? So if I go from 210 to 331, so that would be 210 to 310 is 100 plus 21, so 121. Okay, so no, this is not linear, right? Do you agree these are not equal? Not equal. These are all different, so not linear. Because a common difference, there is no common difference. So definition. Okay, so let's let little r be the growth rate. Be the growth rate. We already have seen little r. Growth rate as a percentage. As a percentage. Then exponential growth, that's what we're defining. Then exponential growth is measured by or modeled by P sub n is going to be P sub 0 times the quantity 1 plus r to the n, where n is units of time, and P sub 0 is the initial amount. Okay, so for example, so suppose the bacteria on a slide, so suppose the bacteria on a slide, number 10,000, so number 10,000, so that's going to be my initial amount. So, and the rate of growth, is 20%. So is 20%. Say every day. Every day. So how many bacteria are on the slide after 2 weeks? So how many bacteria? Are on the slide after 2 weeks. 2 weeks. Okay, so we know that the initial amount, P sub 0, was 10,000, right? So P sub 0, let me write that equal sign better, is 10,000. What is my rate? So my rate of growth is 20%, so that's my little r, right? So little r is 20%. N, so 2 weeks. And since we count this rate every day, do you agree that how many days are in 2 weeks? That's 14. Okay. So what is P sub 14? Well, it should be P sub 0 times a quantity, 1 plus the rate r, raised to the n, right, where in this case n is 14. Okay. So P sub 14 for us will be 10,000 times a quantity, 1 plus, so 20% as a decimal, 0.2 raised to the 14. Okay, so P sub 14 will be 10,000 times 1.2 raised to the 14. Okay, so what I get is 128,391, and that's because I can't have a part of a bacterium, right? Cannot have a fraction of a bacterium. It is a living organism. Bacterium, so I need a whole one, right? Can't have half a person or half a bacterium. Okay, so let's note something. I went from 10,000 to 128,000 in 2 weeks. So let's note. What is the relative change there? If I did final amount, P sub 14, minus initial amount, P sub 0, all over the initial amount. Remember, relative change with respect to the initial amount. What do I get? I get the absolute value of 128,391, from which I'm subtracting 10,000. Oops, wrong color, purple. 10,000. And dividing that all by the initial amount, which is 10,000. Why is this not working? Oh, well, I'd say good enough for government work, but... Oh, okay, there we go. All over 10,000. Okay, so what do we get here? I end up with 11.84. So what does that mean when I plug that into my calculator? So, i.e., that is P sub 14 is 11.84 times as populace as P sub 0. So in 2 weeks, it nearly multiplied by 12. That's substantial. So what I'm going to do here, since this is such a long section, I'm going to cut this section into 2 parts. So I'll see you in the next video.